All right, let's jump right into this material. Today, we're taking those dry, textbook electrical concepts and turning them into a dynamic, field-ready mental model for HVAC troubleshooting. We're moving way past just memorizing definitions. By the end of this, you're going to have a practical, logical toolkit so you actually understand exactly what the electricity is doing inside that unit.
So here's our roadmap. 1. The Golden Fields Rule. 2. Magnetism, relays, and transformers. 3. Capacitors and phase shifts. 4. Decoding service voltages. And 5. The ultimate troubleshooting checklist.
Starting off with Section 1, the Golden Field Rule, measuring safely. The text we're breaking down today stresses one absolute, non-negotiable rule out in the field. Before your probes ever touch a circuit, you have got to set your meter for the correct type of voltage, whether that's AC or DC. Sounds pretty basic, right? But the real-world consequences of getting this wrong are huge. If you're probing a DC control circuit, but your meter is still sitting on AC, you're going to get a totally misleading reading. You'll literally be chasing ghosts, swapping parts that work perfectly fine, and wasting hours of your day.
And this analogy perfectly illustrates why that setting matters so much. Most of the HVAC equipment we work on uses alternating current, or AC. In the US, that operates at 60 Hertz. Think of AC like water violently sloshing forward and backward through a pipe 60 times every single second. Direct current, or DC, which you find in electronic boards and sensors, well, that's like water moving smoothly and steadily in just one direction. You have to know what kind of water you're measuring before you dip your toes in.
Moving on to Section 2, Magnetism, Relays, and Transformers, the invisible forces.
It's actually fascinating to see how beautifully simple this flow is when you break it down. When current flows through a wire that's wrapped into a coil, it creates a magnetic field. It's an energetic chain reaction. Electricity enters the coil becomes a powerful electromagnet, and then that magnet physically pulls or pushes another part. This single concept is what runs your contactors, your relays, your solenoid valves. That coil is literally the muscle making the mechanical movement happen.
Okay, so how do we diagnose this in the field? Here is a rapid-fire tip. If you have the correct control voltage reaching the coil, but you get no pull-in, you've likely got a bad coil or a mechanical jam. Boom, isolated. But if it pulls in just fine and there's no output voltage leaving the device, that almost always points to burned or pitted contacts. Just by watching that mechanical action and checking the voltage across the device, you can instantly pinpoint the failure.
Which brings us to transformers. These guys rely entirely on magnetism too. Most comfort systems use a step-down transformer to take high-line voltage, say 120 or 240 volts on the primary winding, and step it down to about 24 volts AC on the secondary winding for your control circuits. And here's the crazy part. There is normally zero direct electrical connection between those two windings, none. The energy transfers purely through the changing magnetic field in the core. It's magnetic induction doing all the heavy lifting for you.
All right, Section 3, Capacitors and phase shifts, timing and muscle.
But first, a massive safety warning from the text. You know the deal. Capacitors store electrical energy, and they can hold a severe, dangerous charge long after you've pulled the disconnect. You absolutely must de-energize the equipment, verify with your meter that the voltage is actually gone, and safely discharge that capacitor using an approved method before you touch it. The stakes here are incredibly high, so for sure never skip this step.
Okay, safety secured. Now, the source introduces a classic trick for understanding phase shifts. Eli the Iceman. This is one of those tricks that separates the rookies from the pros. Let's break down what this actually means.
In an AC circuit, voltage and current don't always hit their peak at the exact same time. This timing difference, that's your phase shift. For resistive loads, like electric heat strips, voltage and current are perfectly in phase with each other. But for inductive loads, like your motors and coils, current lags behind the voltage. That is the Eli part. In an inductor, E, which is voltage, leads I, which is current. Now, in a capacitive load, like your run capacitors, current actually leads the voltage. That's ICE. I leads E in a capacitor. Your capacitors are literally shifting the timing to give those motors the starting torque they desperately need.
Now, shifting gears from timing to the actual physical pushback in the circuit, we get to impedance, represented by the letter Z. Basic DC circuits just have resistance, right? But AC circuits have impedance, which is the total opposition to current flow, the whole shebang. The main formula to lock in your brain here is Z equals E divided by I. Simply put, impedance equals voltage divided by current.
Let's apply that textbook math to the real world.
Say you're standing in front of a 240-volt motor circuit, and your clamp meter shows it's drawing exactly 10 amps. What's the impedance? 240 divided by 10 gives you exactly 24 ohms of impedance. Running this quick calculation helps you instantly verify if the voltage, the current, and the circuit opposition actually make sense together, or if you've got a failing bearing or a mechanical bind somewhere.
Moving to Section 4, Decoding Service Voltages. Know what to expect.
What is super interesting here is the sheer variety you're going to face out there. Residential is usually a pretty straightforward 120 or 240 volt single phase, but once you step onto a light commercial or industrial roof, you start seeing 208, 277, and 480 volt systems. Here is the absolutely crucial takeaway. A 208 volt system is not the same as a 240 volt system. You always have to confirm the expected line voltage by checking that equipment nameplate. If you're just guessing, your troubleshooting is totally compromised from minute one.
Which brings up a really good question. You see single-phase everywhere in houses, but jump to large commercial systems and suddenly everything is three-phase power. Why do we completely ditch single-phase for those bigger setups?
Well, it comes down to massive efficiency benefits. Three-phase power delivery is just smoother and way more continuous. Because of that, a heavy load can run with significantly less line current. And lower current, that means you can use smaller wires and smaller transformers to deliver the exact same amount of power. It gives you this incredibly smooth starting efficiency, making it an absolute game changer for heavy-duty pumps, massive fans, and big commercial compressors.
But three-phase power comes with a very specific, bold warning you need to remember. If you reverse any two incoming power phases, you will run a three-phase motor completely backward. Just imagine wiring up a massive, expensive commercial scroll compressor, firing it up, and having it run in reverse. No way. It can cause immediate catastrophic damage. You have got to verify proper rotation before you ever let that equipment run continuously.
And finally, Section 5, the ultimate troubleshooting checklist, step-by-step logic. Walk through this exact logical order every single time. 1. Confirm the complaint and check the nameplate so you know the baseline. 2. Verify your power source. Measure that correct AC or DC voltage. 3. Check the control signal. Is the thermostat even asking the unit to run? 4. Test those coil-operated devices to see if the contactor is receiving voltage and pulling in. 5. Check your load side and your capacitors. And number 6, look for the root cause. Seriously, finding a loose wire or a low-voltage short is just as important as swapping a bad part, because if you don't fix the root cause, I guarantee that new part is going to fail too.
So, here's the thought I want to leave you with. The next time you pull off a panel and you're staring at a tangled mess of wires, what's your first move? Are you just going to start blindly swapping parts and crossing your fingers? Or are you going to rely on your new mental model, confident in how electromagnetism and phase shifts actually work, and read the story your meter is trying to tell you? Trust the logic, trust your meter, and stay safe out there.